system that people are doing these things, and I'd rather not do it differently. First one is the purpose. And you know, this week, when I go around and check your pre-labs, you know, if you have something put in there differently than the way I want, I'll just tell you and just, you know, get it right next week. So, purpose. There are three parts to this experiment, parts A, B, and C, and they're pretty much separate from each other in terms of, you know, what you're doing in it. So there's really three purposes, one for part A, part B, and part C. You put all those together in the same purpose section that comes right after the title, then the purpose, put all those three together. And the purpose, it's kind of like what you ultimately are trying to find out by doing that experiment. And in part A, if you look at the procedure on page 24 in your manual, you have the last sentence of the procedure in there. It says calculate the mass percent of sodium chloride in saturated solution. That's the purpose. That's where you're headed towards because of that whole procedure. And that's all. It's not like to learn a technique or anything like that.
What about the bold before, like in the beginning of each part of the procedure, the bold? Would that work? Like
No,
the first part
because for instance, it would be, but part B says collection of calcium carbonate. That's not really the purpose of part B. The purpose of part B is to determine whether or not the precipitate that forms when you mix the two solutions might be calcium carbonate.
Okay,
See how that's different?
So for this first one, you aren't going to mark this out?
No.
Oh, okay.
No, I'm just going to tell you as I go around.
Okay.
And I'm telling you now, so you probably already know. And for part, and also in part B, there's that eggshell. And so that's also part of the purpose, is to find out whether or not eggshells may contain calcium carbonate. And I'm saying may contain. It's not a definitive test, right? You guys remember what you do? You collect the precipitate and the eggshell, and you add a few drops of hydrochloric acid to them. And what you're looking for, remember, is whether or not it fizzes. Right? Remember, does that sound familiar?
Yes, it does.
Okay, thanks. And what I think it tells you in discussion somewhere is that if what you have there is calcium carbonate, it'll fizz. But calcium carbonate is not the only thing that will fizz when you add hydrochloric acid to it. Any carbonate, for example, will be magnesium carbonate, strontium carbonate, what have you. And so, just because it fizzes doesn't mean that it's calcium carbonate. So you're testing to see whether it may be calcium carbonate. On the other hand, what you can say is if it does not fizz, then you know it's not calcium carbonate, it's calcium carbonate. So it works. Then for part C, what you're doing is you're purifying some impure vanillin by recrystallization. And that's pretty much the purpose of that, to purify a sample of impure vanillin with recrystallization. The procedure, most people are getting the procedure pretty well down. One kind of minor mistake or difference that I've been noticing is I ask for either outline format or flowchart. And some people, instead of doing an outline, they're just doing a numbered list, like step 1, 2, 3, 4, 5. And that's really not quite what I'm asking for. I really would like you to try to do the indentations and all that like a real outline, like in the sample pre-lab that I put up there. And the reason for that is if you're indenting subparts, then visually, when you look at it, when I look at it, I can see, okay, this is one thing that you're doing, and then this is the next kind of thing that you're doing. Purpose, procedure. Some people, there's no constant that you need for this lab. Some people put things like molar masses and things like that, because they're not necessary. And if you're not sure, like what constants you're going to need or how you figure out what they are, pretty much any numbers, constants that you're going to need to do the calculations go in the constant section. And sometimes you're going to need to know a constant as part of the lab. Densities are a good example. For instance, you probably haven't looked at it yet, but next week, one of the things we're doing is we're going to take the melting point. You're going to weigh the vanillin that you make today, and you're going to, that you purify today, and you're going to take its melting point range. And what you need, one of the constants you're going to need to know next week is what the melting point range of pure vanillin is. So you should look that up. It ends up, you're also going to be measuring data to allow you to calculate the density of a metal cylinder and they tell you, you know, when you look at it, that it's one of 4 metals. So you should know that in your table of constants next week, you should have the densities of those 4 metals. That's the kind of stuff that goes in constants. Yeah.
I wasn't able to identify the constants for sure. There's the 3 solved experiments in experiment number 2.
There are
So
no,
what I
there are
did
no
was
constants really. Yeah, you don't need a constant section.
I wrote it and I left it kind of blank to where I could fill it in. Are we going to be able to fill certain things in?
Yes, you will, yeah.
Okay,
What I
so
do ask
charge already.
is that, yeah, so there's a CRC handbook in the lab, and I'll show you guys that. And you'll probably want to use it. That's a good place to look up the melting point ranges for the next week and the densities of metals if you don't find them outside the lab somewhere. But what I do ask is that if you're going to do it that way, you're going to fill in the constant when you get into the lab, already have the label for it in the constant section. So for instance, next week, you're going to look up the melting point range of pure vanilla. In your constant section, you should have a melting point of pure vanilla blank. Does that make sense? Because I want to see that you know which constants you're going to do. You don't have the exact numbers yet.
So if it's a boiling point or a temperature, do you want it in Celsius then?
Yeah, we always use Celsius in there. By the way, you may use lighters, okay?
Okay.
We may. For some reason, Samsung's telling me that I told them last semester that they have to use matches in them.
That was true. That was true.
Well, we'll disagree on that. Okay. But you have it recorded now that I said you can use lighters.
Maybe you
Okay.
just told him you don't need his mic.
Maybe it was just him. Maybe sometimes I do that. I say, no, just use Samsung.
Oh.
Don't take me seriously. I do that. But anyway,
Okay.
let me see, so title, purpose, procedure, constants, the data section, the data table. A couple things that I found that people aren't clear on yet is if you're getting a number as a result of doing a calculation, that's not data for me anyway. For me, data is raw data. It's numbers that you get directly in the lab. Any measurements that you take, any observations that you make, those are also data too, and that all goes in the data table. So, for example, in Part A, you're going to measure the mass of the evaporating dish, you're going to measure the mass of the evaporating dish with solution, and so on. That's all data. So you should have entries in your data table for those. However, you're going to calculate the mass of the saturated solution by subtracting out the mass, the solution with the dish minus the mass of the dish. Does that make sense to you? That's the calculation. It's a simple calculation, but it's a calculation, so that doesn't go in the data table, that goes in the calculation section. You're going to end up calculating, if you put it there this way, that's fine. I mean, I'm just letting you know. If you're going to be calculating the mass percent of sodium chloride in a saturated solution, so that's not data, that's calculation. And yeah, a lot of people put it in their data section this week. It's okay, don't worry about it if you did. But next time, just remember, if you're doing anything to the numbers that you get, if you're using them in the calculation, the result of that calculation isn't data anymore, it's calculation. So, as I mentioned, in Part B, you're asked to make, I think, 3 observations. What happens when you mix the 2 solutions together? What happens when you add hydrochloric acid to the filtrate, or the precipitate from the filtration? And what happens when you add hydrochloric acid to the eggshell? That's data, because you're observing it in the lab. So you should have entries in your data table to say, result of adding 2 solutions together, or something along those lines, or just a space and where you can write in what happens. Same thing with that addition of hydrochloric to the two things. That makes sense to you? Data tables, calculations. As I said, calculations for Part A will be the subtractions that you do to get the mass of the dry sodium chloride by itself. Does that make sense? You understand what I'm saying? The subtraction you do to get the mass of the solution by itself, and then the calculation for the mass percent. Part B, no calculations. Part C, you're not going to do any calculations this week. Next week we'll do the calculations. So you don't have to do it.
I have a question. How would you find the mass percent? Because I know that you have to find the mass to get that into the NaC, the mass percent of NaCl in a saturated solution.
So the mass percent of sodium chloride in that solution, what it is, it's how much, what mass of just sodium chloride you have divided by the mass of the solution times 100. That's the
Okay.
calculation.
Okay.
And in your calculation section, it should look something like this. This number, it's, as I mentioned a minute ago, you take after you put this approximately 6 mils of the solution into the dish, you subtract out the mass of the dish from that mass, and that's the mass of the solution. The mass of the sodium chloride, it's after your last flaming. Do you guys know what I mean? Remember? You're gonna, after you evaporate most of the water with the water bath, and you're gonna put it on the flame at wire gauze, and you're gonna flame it at least 2 times, 3 minutes each. After the last flaming, once you've gotten the mass of the last flaming to be within 0.01 grams of the mass of the previous flaming, then stop, take the mass of the last flaming. This is the calculation. This is subtracting how much sodium chloride is in there. So what's happening is you're evaporating all the water, all the sodium chloride is staying behind.
Can also do the N equals M by the mole and then the mass.
No, a lot of people want to use molar mass.
Add two together.
No, because you don't know how many moles you have, right? I mean, these numbers you're just getting directly in the lab. There's no mole mass involved, no moles involved in these calculations. You guys understand it? So it's calculations, and again, I'll look at your pre-labs when we go in, and I'll mention anything that should be different.
Now, if we have, like, say, our equation wrong, are we able to cross it out and rewrite it?
Yeah. Anytime, you cross stuff out in notebooks all the time.
Okay.
Oh, I didn't mention this yet. This week, don't worry about it, but starting next week, only use pen, not pencil. Don't worry, I didn't say that before, I forgot to mention it. And the other thing is, though, if you do make a mistake in your lab notebook, what you do is you put like a single line or maybe an X through it. You still need to be able to read what you wrote, but it's clear that it was crossed out somehow. And then just fill it in. This happens in notebooks all the time, and it's understood that that's what happens. What you shouldn't do, you shouldn't erase it, you shouldn't white it out, scratch it out, anything like that. That's not, you need to be able to see what was there. So that's that. I'll speak about the details of the experiment when we get over there. I'll demonstrate the techniques that you're going to be using. Any other questions on the lab?
When we're going into it, if we have a separate page that we're not really counting for the pre-lab, like you're saying we could put notes and stuff, if we want to put down all the tools we're going to use and stuff like that, is that okay?
Yeah, in your pre-lab unit?
Yes.
Yeah. The only thing is that when you turn it in, what you're going to turn in after you finish are the yellow sheets. You can tear them out, put your name, the section number on at least the first page, staple them together. All the pages should be consecutive. So if there's a crossed out page, still include it. Okay? Because I don't want any page numbers skipped, right? And if you put something like that in there that's not required, still add the yellow page for that.
Okay.
Anything else?
So we don't need to find the mass of the NaCl solute, we just have to find the mass of NaCl and the mass of that
Well,
solution.
it is the solute.
Oh, that is the solute,
It is the
okay.
solute, yeah.
Okay.
I know what you're saying, because when you look up how to calculate the mass percent of solution, it says mass of solute and mass of solution.
Yeah,
That's what they mean by solid.
Oh, okay.
It's what's the solid in the solid. That's what solid's for. Anything else? So, what about the homework? Anybody have any questions?
I forgot.
This is chapter 1, it was, what was it again?
It was a 6-part conversion thing about mercury.
In the other sections, they had questions on that one from chapter 2, if you got there with the X's and the Y's. Everybody seemed to have a question on that one. Does that sound familiar? No?
Actually, the one that I skipped over was in homework 1 where you had 76 pounds of mercury.
Yeah, that's the
and
one.
you had to-
Yeah, that's the one I was talking about.
By the time I got to where you had to convert it in
The cubics and
cubic centimeters.
Yeah,
or
that's the
something
part
like that. But the only one that I got right the first time was how much it weighed per pound.
Yeah, that's
I was
what I got.
I got that.
The first part right.
I got the first 3, and they're just like
So let's see.
Third
I think
part.
it was number 28, I believe.
Converting rates between units. That was just, cost of mercury manometers.
Yeah.
yeah, that thing.
29, yeah.
That's when I was having trouble.
I kind of threw my hands up and went to
So
something
those,
else.
those are the ones that I would like you to bring in.
Oh,
here.
okay.
Because like you're seeing, if you had problems with it, other people did too.
Yeah, I had to give up because I spent probably 30 minutes on it and still could only get the first part right, so.
I got the first 3. I needed the other last 3.
Yeah, it was the last 3. Yeah,
The last 3
I
were the
kinda just skipped
hardest.
And then went into the. And I think it was just part of the old thinking is, why would I have to ever do that? So-
That way lies a dangerous path.
I know, that's why I just closed my laptop and walked away.
So
I did the same
problem
thing
is,
too.
If you guys don't know which one we're talking about, it's problem number 29 in chapter 1. And it at least gives me this, your numbers might be different. A 76-pound flask of mercury costs about $165.
I think everyone got the
That's the
same
one.
number. Right.
And then I did the mistake, I didn't scroll down, so I didn't realize there was more. So I got to the third one and I clicked it and it said it was wrong. I was like, what do you mean it's wrong? And then I scrolled down and saw they had 6 more
It's a cubic centimeter thing. I hated it.
in an inch cubed.
Yeah.
Let's do them. Let's see if mercury. Really? It's different.
Oh, this is my exact same
I
problem.
think I'm up with some funny numbers. Must be at a higher temperature. So, they want, so they basically tell you the density of mercury and the cost per 76 pounds. They want to know, first of all, how much 1 pound costs, and that's just the cost
Yeah.
divided by the pounds. right?
$1.94. $1.94 point, blah, blah, blah.
I want to get the numbers in my calculator so they're there. So I can get it myself. You guys should work along with this. My number, I get $2.17.
Different numbers.
Different numbers, yeah.
Same problem, but
Yeah,
different
same
numbers.
concept,
right? The price of 1 gram of mercury, so. So what I'm gonna do, okay, I'm gonna set this up as a dimensional analysis problem. I'm gonna just look at the units and try to figure it out. And so the question is, how much does 1 gram of mercury cost, right? You know, it says, what is the price of 1 gram of mercury? So how many dollars is equal to 1 gram? And I'm gonna treat this as like a conversion factor, a relationship between dollars and pounds. That is that 1 pound of mercury is $2.17 with my numbers. So what I'm going to do is I'm going to convert grams to pounds and then pounds to dollars, and that'll be the answer. Does that make sense to you guys? So it's like 1 pound is, I think, 453.59 grams, 600. And that was 453 something.
Front of the book, it has 0.6.
0.6, close enough. Actually, this is supposed to be 4 centuries. And that'll give me the answer to that part. So like half of a cent, basically, per gram. The next question is, what is the price of 1 cubic centimeter of mercury? Here, I'm going to use density as a conversion factor. For mercury, I have 13.534 grams of mercury is equal to 1 cubic centimeter of mercury. And the question here is, how many dollars, what's the price of 1 cubic centimeter of mercury? This is the price per gram, right? We figured out how much 1 gram costs. So I can say that 1 gram of mercury is equal to this price. That can convert between grams and cubic centimeters. This can convert between cubic centimeters and grams. That's sufficient. You guys see how?
No, I didn't.
Was that?
I didn't see where you got.
With this calculation that we did here, they had us
Right.
have you do that, like the second step, is the cost of 1 gram of mercury. So another way of saying that is 1 gram of mercury cost or is equal to that much mercury. So, and that's the relationship between grams of mercury and dollars.
Okay. So 1 cubic centimeter of mercury is equal to a gram?
No,
Or
13.5 grams. And the way that we know this is they gave us the density
Okay.
in grams per centimeter cubed. And another way of saying that, the density is 13.534 grams per cubic centimeter. Another way of saying that is 13.534 grams of mercury is equal to 1 cubic centimeter. That's the relationship between cubic centimeters of mercury and grams of mercury. Can you see that? And that's all we need right here.
So where do you get the 13?
They
They gave that to us.
Oh, okay.
They said it in the problem.
Okay.
So so I'm just going to make the units work out. I'm going to go from centimeters cubed to grams, and then grams to dollars. And the first one is the density, I use that. And the second one is this over here. by keeping really carefully keeping track of the units, I see that everything cancels out. I have the units that I need, which is dollars a game. So. About 6 cents, just under 65 cents per cubic centimeter or per milliliter, right? Next one asks, what is the price of 1 cubic inch of mercury? Here we have to set up a relationship between cubic centimeters and cubic inches. What we've calculated here is the cost of 1 cubic centimeter of mercury. So what we can say is that can I erase this? So the way to get the relationship between cubic centimeters and cubic inches is to say that we know, this is one of the things I asked to memorize, 1 inch is equal to 2.54 centimeters. Remember that? That's exact. That's not cubic. The way we make that cubic inches and cubic centimeters is we just cube both sides. So cube this side, cube this side, get 1 cubic inch. So 16.
I got 16.194277.
I get 16.37061. You get this number? See what you got? I've got that number many times in fairly complicated. James, did you get a different number?
Yeah, I keep getting the same one, but I think what I'm doing is
Wait, how are you
I'm not hitting my function keys, but I wasn't
That
doing.
would do it, yeah. Anyway, this now will convert between cubic inches and cubic centimeters, which we need. So we want to know, now the question is, how many dollars is equal to 1 cubic inch mercury? This would be, yeah, price of 1 cubic inch of mercury. And the relationship is that 1 centimeter cubed is equal to that many dollars. 1 inch cubed is equal to that many centimeters. So, making the units cancel out, because we have inches cubed here, we need it in the denominator here. So this 1 inch cubed goes here, in the denominator. This goes in the numerator. Notice, okay, sig figs. This is, do you remember this is an exact relationship. 1 inch is exactly 2.54 centimeters, infinite number of sig figs. So when we cube it, I want to write down everything that I have here to keep it exact. Next, we know that 1 centimeter cubed is this many dollars. Units cancel, we're left with dollars, which is what we want. See exact except for this. $1.06 per cubic inch. You guys with me so far? See how that works out? That's part A. Part B, is continued delivery. Continued delivery.
Will you be one seventy?
What?
Because the one seventy-seven, the low age group is exactly.
Exactly one. They're exact numbers, so that we get.
Oh, that's right. I have a question.
Okay, the next question, part B. My numbers anyway, says it takes 2.950 cubic inches of mercury to make 1 manometer. Find the price of mercury used to make 15 manometers. The first calculating cost of mercury for 1 manometer. So they tell you that it takes 2.950 cubic inches for 1 manometer. How much? First of all, how much does it cost to make 1 manometer? So the question is, how many dollars is equal to 1 manometer? The relationship is that 1 manometer is equal to 2.950 inches cubed of mercury. Do you guys have different numbers? I think it's something.
I had 2.5.
Yeah, something, yeah, right. But so you have to get your own numbers, but just like that. So the relationship here is 1 inch. Oh, I raised. Oh, that's good. Okay. This is the cost right here of 1 cubic inch of mercury. So we can say so I need manometer on the bottom. And then we need inches cubed of mercury on the bottom. That'll be the answer for that part.
Where'd you get the 2.950?
They gave that to me.
Oh, they gave
They
it.
said
Oh.
you need 2.950 cubic inches of mercury to make 1 manometer.
Ah, gotcha, okay.
You good? Any questions on this one? We're almost done. The last question, last part of this question says now, what's the cost of, what does it cost with the price of mercury to make 15 manometers, right? We know how much 1 manometer costs, basically we're gonna take this times 15, right? You guys, is that okay? Can I just leave it like that? So it's
Yeah.
like $45 or something like that. $46.97.
Do the next one, I want to figure it out.
Yeah, you get that one, yeah. The next one, in the saplings, chapter 2, number 4. Anybody else had a chance to start this one? No?
Chapter 3, is that what you said?
Chapter 2,
Oh, yeah.
number 4, X is
I
Y.
don't
You
know.
don't
Oh, no, I don't think I did that one yet. I
So,
think I skipped that one.
yeah, people are finding this one difficult too, so you might want to.
Well, some of the tutorial that they have in there doesn't really help you, because it's like, they say, well, calculate this. I'm like, well, I didn't know where to start in the
Yeah.
first
Yeah.
place.
Why am I calculating this? Let me try to explain it. So what the problem says, okay, there are 2 different compounds. You don't know what, there's 2 elements that make 2 different compounds. You don't know what elements they are, X and Y.
And this was in homework 2?
Yes.
Chapter number 4.
You have 1 gram sample of each. And my numbers, these are going to be different for you probably. Sample 1, sample A contains 0.26 grams of X. Sample B contains 0.35 grams of X. And they give you 1, 2, 3, 4, 5, 6, 7 sets of possible formulas.
X or
X.
Y? Both of them?
I'll talk about that in a minute. Let me finish setting the problem up. So they give you 3 possible sets of formulas with the X's and Y's, and you want to know which of these are possible formulas given this information. And the ones that they give you are for compound A, compound B, no, these are the ones that they give me. I think you'll probably get some slightly different ones there, but it's the same idea. And there may be more than one set that's possible. So the idea is this. Well, first of all, we know there's 1 gram of each compound. So if we have 0.26 grams of X, then there's going to be 0.74 grams of Y. Same idea here, 0.65 grams of Y. So now we know how many grams of X in each compound and how many grams of Y in each compound. But we don't know what elements they are, so we can't use the molar mass, right? If we knew the molar mass, say, of X and Y, we could take the grams of X divided by the molar mass, that would give us the moles of X, the moles of Y, divide them, and that would also the formula of X. Right? Or the ratio, would give us the ratio of X to Y in each of the compounds, but we don't. So what we can do is, what we're gonna do, the way to do this, is to figure out the ratio of X in the first compound and the ratio of X to X in the second compound. The only tool we have to do that is the grams of X, grams of Y. But the thing is, you know this, grams of X is proportional to the number of atoms with the number of moles of X. Do you get by that? Same thing for Y. The thing is, though, we cannot say that, you know, the ratio is 0.26 to 0.35 because we don't know about Y yet. Okay, what we have to do is we kind of have to take Y out of the equation by making it constant. We have to make the amount of Y the same in compound A and compound B. If we do, if we set it up, and I'll show you how we're going to do that, if we can set it up so that the amount of Y in compound A and compound B is the same, then if we take the ratio of the mass of X in A to the mass of X in B, it'll be the ratio of the number of atoms in A, of X in A to the number of atoms of X in B. Try that. The rest of you guys? I mean, that's a lot of talking with no writing. So all we do is we take the grams of X, divide by the grams of Y in each compound, and that'll give us how many grams of X per 1 gram of Y in both compounds. This is in A, this is in B. You guys still with me? What we're going to do now is if we take the ratio of grams of X in 1 gram of Y in B to the grams of X to 1 gram of Y in A, the grams of Y are constants, they cancel out, and that'll give us the ratio of the grams of X in B to the grams of X in A, which is the same as the number of atoms of X in B, number of atoms of X in A. You guys buy all that? Let me show you, see if you buy.
So, like, when you're talking about it as a ratio, so you have 0.35 grams of X per 1 gram of Y, so you would almost get about 3X per Y.
Let's see what we get.
We're to 53 grams, we're to 53.
I'd say 0.35 divided by 0.65. That's 0.538 over 1. You see what I'm doing there?
Why is B on top of A?
It could have been the other way, but I noticed that this number is bigger than that number, and I like whole numbers.
Okay.
If you like decimals, or, you
Oh,
know,
no, I was just wondering if there was
No
a reason
reason.
other than that.
personal preference.
Okay.
about 1.5 grams of X in B per every 1 gram of X in A. Again, it's important that we're keeping the amount of Y the same so we kind of can get that out of the way. Right? And because we know there's 3 grams of X in B for every 2 grams of X in A, keeping Y constant, we know there are 3 atoms of X in B for every 2 atoms of X in A, keeping Y constant. Okay? Keeping Y constant is really important. So now we can go, write that down. Now we'll go through the possibilities it gives. Finish writing the first piece.
So if y is a constant, would it mean that y is the same?
We have to, yeah, that's where I'm going with this.
Oh, okay.
Over here, we can't just look at this and see 3 to 2. We have to make sure y is the same. Like here, it's not, so we have to make it the same.
Oh, okay. So that's all it means for it to be a constant, is for it to be the same? Okay.
Yes.
Could you repeat what you just said?
Yes. Are you guys finished writing that down?
Yeah.
So,
Well, I guess I got lost where the grams go to atoms, like for every gram
Oh.
is an atom, is that what you?
think about it this way, right? We know, let's say if it's hydrogen, we know that 1 mole of hydrogen weighs 1.0079 grams.
That's the molar mass.
That's the molar mass, right? That's how much 1 mole weighs. So if we have 2 grams of hydrogen in one compound and 1 gram of hydrogen in another compound, that means we have 2 moles of hydrogen in the first and 1 mole in the second, which means we have twice as many atoms in the first as in the second. So the ratio of the grams of an element in one compound to the grams of that element in the second compound, it's the same as the ratio of the numbers of atoms, as long as you keep the number of the other elements the same.
Constant.
Constant.
Can you explain why is you're keeping that as a constant?
I could have kept X constant.
You need one of these constant.
Yeah, you have to be 1. I chose Y.
Okay.
If you chose X, it would work just perfectly fine.
Okay.
You guys understand? It doesn't matter which one you keep constant. One has to be constant, then you get the ratio of the other. Are you guys with me up to here?
So would the answer be the third one down?
Well, there's more than one
down?
answer. There's more than one possibility.
Oh, okay, because I see 2 possibilities. but-
Yeah, what I'm gonna do now is go through them.
Oh, okay.
So what we're gonna do is compare the sets of possibilities, at least they gave me for my answers, to this. What we're looking for is Y constant and 3 B's, 3 X's in B for 2 X's in A. So X2, Y3 would be good. I mean, X2 here and X3 here works. Y is constant, but 3 to 4 is not 2 to 3. It's 3 to 2. You guys see what I'm saying? So we can cross that one off. That won't work. Y is not constant here, right? The way we get it constant is we multiply both of these subscripts by 2 to get, Y constant. That makes sense? Do you guys see what I did there? So I multiply that by 2 and that by 2. And the reason is I wanted to get Y to be the same. Now if we look at X4, Y6, that's 3 to 2 and 2 to 3. That'll work. You guys see what that is? No? There's, it's not like, okay. So what we're looking for is 3 X's in B for every 2 X's in A, keeping Y constant. By multiplying these by 2, I kept Y constant between the 2 compounds, and we ended up with 6 X's in B for every 4 X's in A. That's the same as 3 X's in B for every 2 X's in A. And so that's a possibility. that works. Next, this one here, y is constant, 3 x's in b with 2 x's in a. That's good just as it's written. Here, y is not constant. How do you think we're going to get it constant?
That's one side by 3 and the other by 4.
Yes, that's right. Just find the least common multiplier. So multiply these by 4. You get x4, y12, and x3, y12. Is that okay? No? Oh, it doesn't work, yeah, but you understand what I did there? I have to get y the same. Okay, this whole thing, we have to keep y constant. That's the only way it's going to work. It's not the same between the two compounds here. There's 3 y's here and 4 here, right? So, the only way I can make it the same in both is by multiplying both subscripts by some number. Here, that's the smallest number that I can get is 12. So multiply these by 3, these by 4.
This is like the first thing was to make y constant, right?
Yeah.
Or whatever you pick constant here, make constant.
Yeah, or if you picked x, then you make an x constant. But either way, this is not 3 to 2. See, that 3 doesn't work, so it doesn't work. Here, y is already constant, and 1 and 1. This is not 3 to 2, so that doesn't work. Y is constant here, 5 to 5, and x is 3 to 2, so this one is also 3. Good for that. Y is constant, x is 3 to 1, not 3 to 2, that doesn't work. So the ones, at least for my problem, they gave me the ones that work for this one, and this one. That's good. All this is really getting at is that you understand that, how the ratio of the masses relates to the ratio of the numbers of atoms to the numbers of moles.
So in Kaplan, you can pick any one of those?
No, you have to pick them all. If you only pick 2 of them, they'll say incorrect, there's still another. I think we're out of time. Is there time to go to the lab?